Hi everybody. Today we're going to go a little bit further into circuits. We've been using pretty simple circuits in class. One battery, a couple of wires, and a light bulb. But I'm sure you realize that circuits in the real world sometimes are a little bit more complex. We often plug more than one object into our outlets, so we usually have more complex circuits out there than just those we've been using in class. So we want to be able to solve problems with those types of circuits. In order to do that, we have to be able to visualize the circuit, draw some nice, neat circuit diagrams. We want to be able to differentiate the way in which we can configure the circuit, how we connect the objects in the circuit to the battery or a voltage source. And finally, we still want to be able to calculate some of those electrical quantities of the circuit, voltages across resistors, currents through the circuit. So we'll still use Ohm's law to solve those problems. Okay, before we might go much further, we really want to know what a circuit is. We know that we had a battery, a light bulb, and a bunch of wires in class. We put them all together, and when we put them all together, ooh, magic, the light bulb went on. When we put all those components together, we formed that circuit. There are requirements to have that circuit. You must have a battery or voltage source, you must have conducting or connecting wires, and you have to have a resistor or something in the circuit that's going to use up that energy or dissipate power. When you have a complete path, in order to allow that current to flow and for the energy to be transferred from the battery to the object in the circuit, you have a closed circuit. If for some reason one of your wires breaks or everything is not connected as needed, there's no complete path for any current to flow. So even though you have the required objects, you have the battery, you have the light bulb, and you have the wires, if they're not all connected so that current can flow, you have an open circuit. When we start representing circuits, we want to be able to use a nice, neat diagram to create a visual representation of the circuit. It's nice to be able to draw things like these here, where we understand what a battery is and it's connected just like we connected this circuit in class. But when we need to draw them and understand what's going on, sometimes it's easier if we create a schematic or a diagram of the circuit, sort of like an architect's blueprints, something that looks more like this. And if we know the symbols for each of those things, we can create diagrams where we know what everything is, and it makes this a little bit simpler for us to solve some of our problems. So at this point, this is where you need that circuit's basic worksheet. You want to be able to fill in the circuit symbols, the diagram symbols that you're going to use for each of the devices that we have in our circuit, because you want to be able to draw those diagrams. So first we'll start with the battery. Remember, a battery provides that voltage difference in the circuit to cause the current to flow. We represent a battery with the symbols shown here. Two lines, one longer represents the positive terminal, one shorter represents the negative terminal. Our battery provides the voltage, and it, remember, is measured in units of volts. V. Right. A conductor. A conductor is a wire that allows those electrons to move freely. It's essentially the path that the current flows through. Now we know that that's been provided by wires, but sometimes we don't want to draw the wires exactly as they are because they're not always very neat. So we always want to represent our conducting path as a nice straight line. Now, even though we really don't have a measurement of the conductor, what we realize is the current flows through the conductor. So usually when we're thinking about that conducting path, we're thinking about current flowing through the path. And remember, current is measured in the units of amperes, or what we call amps, represented with an uppercase A. Okay, the next thing we might put into our circuit is a switch. It's probably not the best thing if you had to turn on and off your light every time in your room by maybe unscrewing or screwing in the light bulb. So we put switches in. Switches allow us to open or close the circuit. If our switch is closed, so for example in your house, if your light switch is on, it allows current to flow. If the switch is open, for example in your house your light switch is off, it opens up that circuit temporarily until the switch is closed again and current can't flow. It opens up a circuit so you no longer have a closed circuit. Switches are in the conducting path, but we like to make sure that we know they're there. So instead of just drawing the line and having it be continuous, we represent the switch as these little circles with a line in between. That way, if the switch is closed, we know that it's still a nice closed path, but we know we could open it up and create an open circuit at any time simply by opening up the switch. Switch does not have any units of measurement. Its sole purpose is to be able to stop current flow in the circuit. All right, our resistor. Our resistor is any object in the circuit that consumes the energy that the battery provides to the circuit. This could be our light bulb. It could be your toaster oven, your coffee maker. It could be anything that is attached to the battery or the voltage source that's going to use that energy. When we represent a resistor in a circuit, we use this little squiggly line here. It's sort of like a zigzag or a sawtooth. And if you think about it, it kind of makes sense. A resistor resists the flow of current coming through it. So a nice straight line would indicate a nice smooth and easy path. This sort of sawtooth or zigzag line makes it seem like it would be a little harder to get through. And that's that representation of the fact that the greater the resistance, the harder it is for the electrons to move through. Remember, anything that's a resistor is represented by its resistance, which is measured in ohms. Right? And the unit of measurement is that great omega that we use to represent ohms. Now, we've been using an awful lot of light bulbs or lamps in class because it makes it very easy to see that current is flowing in the circuit if we see a light bulb turn on. A lamp is still just a resistor. It's consuming the energy from the battery. You can draw it if you want as a lamp to indicate it's a special type of resistor that we might use. And the only way we do that is to add a little circle around the resistor zigzag. But if you just want to represent anything that consumes energy in the circuit as a resistor, that's fine. You don't necessarily have to make a specific drawing for a lamp. The last thing that we might put into our circuit is a meter. A meter is used to measure those electrical quantities about the circuit, a voltage across something or a current through something. When we draw meters in, we add them into the circuit to let us know that they exist. The two types of meters that we're going to be using, or at least the two types of measurements, are voltmeters, which measures voltage, and ammeters, which measures current. We won't be using specific meter types like this in class. We will be using a multimeter, which means it measures multiple types of electrical quantities. If you want to put these into the circuit though and show them, you have to remember that voltage is measured across something. So for example, if I had a battery and a resistor, and I wanted to measure the voltage across this resistor, I would put my voltmeter actually across it. If I then had an ammeter in my circuit because I wanted to measure current, remember, moves through the conductor. So I would have to put the ammeter in the current path. So in this case, say for example I have my battery and my resistor. If I wanted to measure the current going through the path, I would actually have to put my meter in the path in which I'm measuring the current. Once again, the meters don't have any measurements themselves. They are just a way of measuring the units that we're looking for. Okay, so let's draw one real quick to just make sure that we're okay. We have a battery here with a light bulb and a switch. So use your finger, go around the path, make sure it's complete. I started the positive terminal of the battery. There's my positive terminal, my long line. I would come out and I would start my conductor, my wire. I would get to a switch, so I would draw my 2 circles in my path. I would look and see whether or not my switch is open or closed. In this case, you can see my switch is open. I would continue my path, come around here to my light bulb, which I'm always going to consider them all to be resistors. I'm going to draw my resistor. I'm going to keep going to my conductor until I come back to my negative terminal of my battery. And I have a complete circuit diagram. Okay, so now why do we need to know these? As we start to get more complex circuits, we need to be able to visually represent them. So here's the deal. When we connect 2 or more electrical devices, meaning 2 or more resistors, things that want to use energy in a circuit, we have 2 ways in which we can connect the devices. If we put the devices all in one loop, one after the other, meaning there's only one loop, one path that comes out of the battery, goes through all the devices, and comes back to the battery again, those devices are connected in series. They come one after another, just like a series. If, on the other hand, we create multiple loops or multiple paths for the current to flow, meaning current goes through each one of the devices separately, we create a parallel circuit. Those devices are connected in what we call a parallel way. Now, there are advantages and disadvantages to both, and we'll talk about them a little bit more in class. But now we just want to go through about how to solve problems and how to calculate some of those electrical quantities when we have both of the configurations. So let's look first at series circuits. The rule of thumb to remember with a series circuit is remember that the battery wants to give up all its energy. And when we talked in class and we did problems with Ohm's law so far, we've been saying that if there's just one device in the circuit, all the voltage from that one battery is dropped across the one device in the circuit. So if I had our light bulb in class, for example, if it were connected to a 1.5 volt battery, the voltage drop across the light bulb would also be 1.5 volts. So what happens in a series circuit is you have multiple devices that have to share that 1.5 volts or whatever the voltage is of your battery. So here are the rules that make it easy if you can remember, and it will help you understand how series circuits work. So the thing is, because they're connected all one after the other, there's only one single path for the current to flow. As a result, if for whatever reason there's a switch in there, or there's a break in the wire, or something breaks, any break in one device can cause the open circuit, because as soon as you have a break anywhere in this type of series circuit, current can no longer flow. The current in each device is the same amount. Because there is only one path to go, there can only be one value for the current flowing through all the devices. And then last but not least, the voltage drop across each device depends on the resistance of the device. But you have to remember that the battery wants to give up all that energy. So when I look at the voltage drop across each of the devices and I add that up, that should still sum up to the voltage of the battery. So here's how we approach solving the problems. Because when you connect multiple devices in a circuit, the battery doesn't know that there are multiple devices out there. It just sees one big resistor that wants some current. So what we have to be able to do is figure out what that one big resistor looks like to the battery. And the way we do that is by calculating something that we call equivalent resistance. It is a one resistor representation of all the resistors in the circuit. Once the battery knows what that equivalent resistance is, it's going to produce the necessary current to supply that one equivalent resistor. So when objects are connected in series, the equivalent resistance is simply found by adding the resistance values of all the devices in the circuit. So when you have resistors in series, the equivalent resistance is always larger than any individual resistor. And as a result, the current's going to go down the more resistors you add. And you remember when I did that quick demonstration in class, when we were comparing how our graphs looked. When I added 2 light bulbs to my circuit with my battery, they got very dim, and that was because it had less current. So let's look at an example. Here we have a series circuit example. We have a 9-volt battery, and we have 3 light bulbs in the circuit. One is a 3 ohm resistor, one is a 6 ohm resistor, and one is a 9 ohm resistor. We want to be able to find the current that's flowing through the circuit, and we want to be able to determine the voltage drop, or essentially that measurement of the energy consumption of each of the light bulbs. They're different types of light bulbs, so they're probably going to consume different amounts of energy. So here's the way to always check to make sure you know if it's a series circuit. Use your finger, follow the path. If you come out of the battery and go and follow the path all the way around the circuit through all of the devices and back to the battery again, if your finger never needs to make a decision about which way to go, doesn't hit a fork in the road, you have a series circuit. Okay, so let's see what we're going to do. The first thing we're going to do, of course, is we're going to draw our circuit diagram, because we want to be able to create this visually so that we can see everything as a nice circuit. So remember, I had my 9-volt battery. And I'm going to draw my battery, and I know that's 9 volts. I have my positive and my negative terminal. I draw my conducting path. I come out, I have 1 resistor, I have the 2nd resistor, and I have the 3rd resistor. Go around the rest of the circuit, come around and back to my battery. Okay. My first resistor, I'm going to call it R1. My 2nd resistor, R2. 3rd resistor, R3. Now remember, these are all just lamps, but they use the energy that is provided by the battery, so as a result, they're resistors. The value for this one is 3 ohms. The value for this one is 6 ohms. And the value for this one is 9 ohms. Okay, so now what we have to do is we have to be able to figure out how much current is going to be sent out by the battery to supply the energy to these 3 resistors. Remember, the battery only sees the 3 resistors as one equivalent resistance. So that's what we have to do, is we have to go out first and simplify this down to one of those simple circuits that we're used to looking at. 1 battery, 1 device, but that 1 device is really an equivalent device. So what we're going to do is we're going to take this, all right, and we're going to create an equivalent resistance for these 3. All right, so if it's in series, the equivalent resistance equals the sum of the individual resistances. So I would take my 3 ohms plus my 6 ohms plus my 9 ohms, and that's 18 ohms. Alright, so this is the same thing as saying I have a circuit that looks like this. Here's my resistor. I come back. Alright, I have a battery, and I have an R equiv. This now looks like something that we can solve. Right? So what I want to do is I want to be able to figure out, first of all, the current. There's only one current moving through this circuit because there's only one path. So the way I can do it is I can use Ohm's law. Still go out and use those. Those rules are still completely valid for the way we solve problems. But I rewrite Ohm's law a little bit differently because I know this is a more complicated circuit. So what I do is instead of saying I equals V over R, I add a little subscript. I say I total, meaning the total current in the circuit is equal to the voltage of the battery divided by the equivalent resistance. That way I really know I'm talking about a circuit where I have multiple devices. If I plug in my values now, I have my voltage of my battery is still 9 volts, and my R equivalent is equal to my 18 ohms. Right? So I know the current in my circuit is 0.5 amps. Right? So I know in this circuit, I have an I of 0.5 amps. Alright, so that answered my first question. What is the current in the circuit? There is only one, and that's its value. But then it asked me for what the voltage drop was across each resistor. So here's where I have to go back and say, I can use Ohm's law also for each individual device in the circuit. So let me look at this. Let me figure out what the voltage drop is across the 3 ohm resistor. That's going to equal the current flowing through the resistor times the resistance. So I know that is my 0.5 amp, because it's the same for every device in a series circuit, multiplied by my 3 ohms. That tells me it's 1.5 volts. So I lose 1.5 volts as my current goes through that 3 ohm resistor. My current continues through them, and now it goes to the 6 ohm resistor. The voltage drop across the 6 ohm resistor is equal to the current through it, which is the same, multiplied by its resistance, 6 ohms. So this guy is 3 volts. And last but not least, my current is now going to move through my 9 ohm resistor, and I want to know the voltage drop across it. So the voltage drop across my 9 ohm is the current through it times its resistance, 0.5 times 9 ohms equals 4.5 volts. Here's where I go and check and make sure I did some math right. The important thing to remember in series circuits, the sum of the voltage drops across all of the resistors has to equal the total voltage of the battery. So that means if I have a 9 volt battery, 3 resistors in my series circuit, when I add up the voltage across each, it should sum up to 9 volts. Well, 4.5 plus 3 is 7.5 plus 1.5 is 9. 9 volts. So yes, I must have done something right. You could also continue and use the rest of what we learned in addition to Ohm's law about power. You could calculate the power dissipated by each of these resistors by doing power equals voltage times current. You could do figuring out, based on any of the information you knew, be it voltage and current, you could figure out power also dissipated, which is that other way that we look at how energy is consumed by a resistor in a circuit. Okay, so now let's look at parallel circuits. What are the rules for parallel circuits? Well, the idea with the parallel circuit is that the voltage drop across each of the devices in the circuit is the same. Unlike with the series circuit, where the current is the same through the entire circuit. Here, the voltage drop is the same across every device in the circuit. And that's because if you look at it, if the voltage from here to here has to be the same as the voltage from here to here, has to be the same as the voltage from here to here. It's a voltage drop that all, roughly, when you think about it, are measured from the same point. So you have to have the same voltage drop across each device in a parallel circuit. Some of the differences, though, is if we break just one of the paths in a parallel circuit, it doesn't stop the whole current flow. It just creates an open circuit in that path. So as a result, current can still flow through the remaining paths. The amount of current going through a path is going to depend on the size of the resistor in that path. But the rule is that more current will move through the path with least resistance. So when you have devices connected in parallel, that's a good way to check to make sure that you're doing some of your math okay. If you look at something and you calculate the amount of current going through it, it should have a larger number if it's the smaller resistor. Alright, and the last important part is going to be our check. Just like we could say that in a series circuit, the voltage is across each of the resistors when we sum them up equals the voltage of the battery. In this case, for parallel circuits, we're going to say that the current through each of the resistors, when it is summed up, should be equal to the sum of the current actually sent out by the battery. Okay, and just like series circuits, the battery doesn't see them as the resistors as individual resistors out there. It sees it as one equivalent resistance. So as a result, we have to be able to calculate equivalent resistance, and it's different using parallel circuits than it is with doing series circuits. The equivalent resistance is found by adding all the inverses of the individual resistors and then inverting it. Alright, so this is how you would figure it out. You actually have to flip over each of the resistance values, and that gives you the flipped over value of the equivalent resistance. You have to flip that over at the end. Now I'm going to do an example with fractions, but when you actually do this in class, I'm going to show you a short trick with your The thing to remember is when resistors are connected in parallel, the equivalent resistance is always smaller than any individual resistor. So that's different than series. When you connect them in series, the equivalent resistance get bigger and bigger as you add more resistors. For parallel combinations, the equivalent resistors get smaller and smaller as you add more resistors. Okay, so let's look at an example. Let's take our exact same values, our 9-volt battery and our 3 lamps, one with 3 ohms, one with 6 ohms, and 9 ohms. And this time we're actually going to connect them in parallel. We want to be able to determine, again, the current in the circuit and in each light bulb, and the voltage across each resistor. Okay, so once again, the first thing we want to do is we want to draw ourselves a nice circuit diagram to make it a little easier to know what's going on. So here, I'm going to have my 9-volt battery. From our picture, remember we come out of our battery, and what happens now is our conductor splits, our path splits. It goes first down this way to the 3 ohm, comes out and goes here again to the 6 ohm, but that one also splits again and goes to the 9 ohm. Alright, so the way to remember to know whether or not you have a parallel circuit is you do exactly the same thing. You follow the path with your finger, and if at any time you have to make a decision about which way to go, you have a parallel circuit. Alright, so here I still have R1, R2, and R3. All right, my R1 is 3 ohms. My R2 is 6 ohms. And my R3 is 9 ohms. Okay, so here's the deal. We have to remember that our battery is first going to look at an equivalent resistance to see how much current it should send out into the circuit. So it sees this as one equivalent resistance. So let's redraw our circuit to make sure that we're okay with that. We have our battery, and now we have just one resistor. So it's back to, again, one of those simple circuits that we're used to. We just have to figure out what the equivalent resistance is. So we would say that 1 over R equiv is equal to the sum of the inverses. So 1/3 plus 1/6 plus 1/9. Alright, now I did some fraction work. I have to put this all over a common denominator. The common denominator is 18, so I get essentially 6/18 plus 3/18 plus 2/18, and that gives me 11/18. If the fractions are scaring you, don't worry. I'll show you how to do it with your calculator in class. But remember, this is 1 over R equiv. In order to find R equiv, I have to invert that. So that would actually give me 18 over 11. Which, when I put that into a decimal, is going to give me about 1.636 ohms. I'm going to carry these out a few decimal places, because when we start doing too much rounding too early, some of those checks that we might like to do, the math won't quite add up. So you want to make sure you carry your decimal places out a few more than you're going to do when you do your final rounding. Alright, so I'm going to do the same thing. I want to know what the current is that's flowing through this circuit. So again, I can use Ohm's law, but I'm going to use that special thing where I'm going to say it's I total V over the battery divided by the equivalent resistance. Alright, so this one is going to tell me it's my 9 volts divided by my 1.636 ohms, and that would give me a total current of 5.5 amps. That's what the battery is going to send out to that equivalent resistance. Now when it gets actually into the real circuit, what's going to happen is that I total is going to come here, some of it's going to go here, some of it's going to go there. That's going to continue to flow, and some of it's going to go here, some of it's going to go there. So I'm going to get 3 individual currents going through each of the resistors. When it comes back through here, this one adds back up with that one, and we get the total going back here, which adds back up with that one, and should go back and be the total amount of current that came out of the battery. So let's check and make sure. We're going to figure out the current going through each of the resistors. So here we go, and we say, well, the current going through the 3 ohm resistor is equal to the voltage across the resistor divided by the resistance. Here's where you're going to say, what's the voltage across the resistor? You have to remember the rule for a parallel circuit. The parallel circuit tells me the voltage across each individual resistor is the same as the voltage of the battery. So if the voltage of my battery is 9 volts, the voltage across my resistor here is 9 volts. So 9 volts divided by 3 ohms equals 3 amps. Alright, the current across my 6 ohm resistor, same thing. It's the voltage across the resistor, 9 volts divided by my 6 ohms, 1.5 amps. And last but not least, the current through my 9 ohm resistor equals the voltage across it, 9 volts, same as the battery, divided by my resistance, 9 ohms, tells me 1 amp. So here's where I want to check and make sure I did my math okay. The sum of the currents traveling through each resistor has to equal the total current sent out by the battery. So 3 amps plus 1.5 gives me 4.5, plus another gives me 5.5 amps. So I must have done something right. All works out. And again, you could still use your power equation if you wanted to figure out any of the power dissipated by the resistors. Alright, so I'm sorry, I know this one was long, but let's just review and make sure that you get what you need to know in order to solve series or parallel circuits. The first thing you want to do is be able to figure out if the resistors are connected in series or in parallel, and use your finger as the test. Come out of the battery, follow through each of the devices. If your finger never has to make a decision which way to go, it only goes one path, you have a series circuit. If it ever has to decide, do I go right or left, or do I approach a fork, you have a parallel circuit. You have to then take that resistance value that is represented by all of the resistors, that equivalent resistance. You have to find out what the battery thinks the resistance is. Calculate that using either your series or your parallel resistance. Determine the amount of current produced by the battery based on that equivalent resistance. Alright, if you're going in a series circuit, that current's going to be that current through every resistor. If you're going through a parallel, that current's going to divide up, and some's going to go through each resistor. The one with the least resistance will get the most current. The one with the most resistance will get the least current. Use your rules to figure out the voltage across or the current through the individual resistors. This means that the current through each resistor in a series circuit is the same. The voltage across each resistor in a parallel circuit is the same. And then last but not least, use those rules to check your work. For series circuits, sum up the voltage drops across each resistor. It should equal the total voltage of the battery. For parallel circuits, sum up the current going through each resistor. It should equal to the total current that you calculated when using the equivalent resistance. Okay, I hope that helps. Be prepared, because we'll start with problems when you come back. Thanks.